Learning objectives. In this chapter, the user will learn the following in detail. Basic software quality parameters and its metrics, software configuration change, types of errors, quality management models, ISO, PIEs, IEEE, CMM. Basic software quality parameters and its metrics. Software quality. A quality software has two features. 1. Conformance to its specification. 2. Fitness for its intended purpose. Quality is a multi-dimensional construct. It's represented by a three-dimensional solid. Software metrics are used to measure the software quality. Metrics are classified into two types. 1. Predictive, used to make predictions about the software. 2. Descriptive, describes the state of the software at the time of measurement. McCall and Boehm adopted different approaches to metrication. Boehm methods are based on checklists requiring yes or no answers. For example, structuredness measured by questions such as, have the rule for transfer or control between modules been followed? Yes, no. Are modules limited in size? Yes, no. Do all modules have only one exit point? Yes, no. A well-structured program will produce positive answers to such questions. McCall's approach is more quantitative, using scores derived from equations. McCall's software quality factors. McCall has 11 factors that are grouped into three different categories that are product operation factors, used to measure how well it runs, correctness, reliability, efficiency, integrity, and usability. Product revision factors, how well it can be changed, tested, and redeployed. Maintainability, flexibility, testability. Product transition factors, how well it can be moved to different platforms and interface with other systems. Portability, reusability, interoperability. McCall's quality factors category, product operation factors. Correctness. A program satisfies its specification and fulfills the customer's mission objectives. Reliability. A program can be expected to perform its intended function with required precision. Efficiency. The amount of computing resources and code required by a program to perform its function. Integrity. Access to software or data by unauthorized persons can be controlled. Usability. Effort required to learn, operate, prepare, input, and interpret output of a program. Maintainability. Effort required to locate and fix an error in a program. Flexibility. Effort required to modify an operational program. Testability. Effort required to test a program to ensure that it performs its intended function. Portability. Effort required to transfer the program from one hardware and/or software system environment to another. Reusability. A program can be reused in other applications related to packaging and scope of the functions that the program performs. Interoperability. Effort required to couple one system to another. ISO 9126 quality factors. ISO 9126 standard was developed to identify quality attributes for computer software. The standard identifies 6 key quality attributes. Functionality. Software satisfies the stated needs as indicated by the sub-attributes. Suitability, accuracy, interoperability, compliance, and security. Reliability. Amount of time that the software is available for use as indicated by the sub-attributes. Maturity, fault tolerance, recoverability. Usability. Software is easy to use as indicated by the sub-attributes. Understandability, learnability, operability. Efficiency. Software makes optimal use of system resources as indicated by the sub-attributes. Time behavior, resource behavior. Maintainability. Ease with which repair may be made to the software as indicated by the following sub-attributes. Analyzability, changeability, stability, testability. Portability. ease with which the software can be transposed from one environment to another as indicated by the following sub-attributes: adaptability, installability, conformance, replaceability. A framework for product metrics. Measures, metrics, and indicators. These three terms are often used interchangeably, but they can have subtle differences. Measure provides a quantitative indication of the extent, amount, dimension, capacity, or size of some attribute of a product or process. Measurement, the act of determining a measure. Metric, a quantitative measure of the degree to which a system, component, or process possesses a given attribute. Indicator, a metric or combination of metrics that provides insight into the software process, a software project, or the product itself. The accompanying figure shows the software metric collection process. Purpose of product metrics. Aid in the evaluation of analysis and design models, provide an indication of the complexity of procedural designs and source code, facilitate the design of more effective testing techniques, assess the stability of a fielded software product. Activities of a measurement process. Formulation. The derivation, that is, identification of software measures and metrics appropriate for the representation of the software that is being considered. Collection. The mechanism used to accumulate data required to derive the formulated metrics. Analysis. The computation of metrics and the application of mathematical tools. Interpretation. The evaluation of metrics in an effort to gain insight into the quality of the representation. Feedback. Recommendations derived from the interpretation of product metrics and passed on to the software development team. Characterizing and validating metrics. A metric should have desirable mathematical properties. It should have a meaningful range, that is from 0 to 10, for example. It should not be set on a rational scale if it is composed of components measured on an ordinal scale. If a metric represents a software characteristic that increases when positive traits occur or decreases when undesirable traits are encountered, the value of the metric should increase or decrease in the same manner. Each metric should be validated empirically in a wide variety of contexts before being published or used to make decisions. It should measure the factor of interest independently of other factors. It should scale up to large systems. It should work in a variety of programming languages and system domains. Goal-oriented software measurement. Goal, question, metric, GQM paradigm. GQM technique identifies meaningful metrics for any part of the software process. GQM emphasizes the need to establish an explicit measurement goal that is specific to the process activity or product characteristic that is to be assessed. Define a set of questions that must be answered in order to achieve the goal. Identify well-formulated metrics that help to answer these questions. GQM utilizes a goal definition template to define each measurement goal. Attributes of effective software metrics. Simple and computable. It should be relatively easy to learn how to derive the metric, and its computation should not demand inordinate effort or time. Empirically and intuitively persuasive. The metric should satisfy the engineer's intuitive notions about the product attribute under consideration. Consistent and objective. The metric should always yield results that are unambiguous. Consistent in the use of units and dimensions. The mathematical computation of the metric should use measures that do not lead to bizarre combinations of units. Programming language independent. Metrics should be based on the analysis model, the design model, or the structure of the program itself. An effective mechanism for high-quality feedback. The metric should lead to a higher quality end product. Metrics for the analysis model. Functionality delivered provides an indirect measure of the functionality that is packaged within the software. System size measures the overall size of the system defined in terms of information available as part of the analysis model. Specification quality provides an indication of the specificity and completeness of a requirement specification. Function points used for measuring the functionality delivered by a system. Using historical data, function points can be used to estimate the cost or effort required to design, code, and test the software. Predict the number of errors that will be encountered during testing. Forecast the number of components and/or the number of projected source code lines in the implemented system, derived using an empirical relationship based on countable, direct measures of the software's information domain, assessments of the software's complexity. Information domain values. Number of external inputs. Each external input originates from a user or is transmitted from another application. They provide distinct application-oriented data or control information. They are often used to update internal logical files. They are not inquiries. Those are counted under another category. Number of external outputs. Each external output is derived within the application and provides information to the user. This refers to reports, screens, error messages, etc. Individual data items within a report or screen are not counted separately. Number of external inquiries. An external inquiry is defined as an online input that results in the generation of some immediate software response. The response is in the form of an online output. Number of internal logical files. Each internal logical file is a logical grouping of data that resides within the application's boundary and is maintained via external inputs. Number of external interface files. Each external interface file is a logical grouping of data that resides external to the application but provides data that may be of use to the application. Function point computation. Please refer to the statement on screen. Metrics for the design model. Architectural design metrics. Its emphasis is on the architectural structure and effectiveness of modules or components within the architecture. They are black box in that they do not require any knowledge of the inner workings of a particular software component. Hierarchical architecture metrics measure the complexity of software components and other characteristics that are bearing on quality. Structural complexity. S of I equals F out squared of I, where F out of I is the fan out of module I. Data complexity. D of I equals V of I divided by F out of I plus 1, where V of I is the number of input and output variables that are passed to and from module I. System complexity. C of I equals S of I plus D of I. As each of these complexity values increases, the overall architectural complexity of the system also increases. This leads to greater likelihood that the integration and testing effort will also increase. Shape complexity. Size equals n plus a, where n is the number of nodes and a is the number of arcs, allows different program software architectures to be compared in a straightforward manner. Connectivity density, that is, the arc-to-node ratio, R equals A by N, may provide a simple indication of the coupling in the software architecture. Interface design metrics focus primarily on usability. Specialized object-oriented design metrics measure characteristics of classes and their communication and collaboration characteristics. Metrics for object-oriented design. Size, population, a static count of all classes and methods. Volume, a dynamic count of all instantiated objects at a given time. Length, the depth of an inheritance tree. Coupling, number of collaborations between classes or the number of methods called between objects. Cohesion of a class is the degree to which each set of properties is part of the problem or design domain. Primitiveness, a method in a class is atomic, that is, the method cannot be constructed out of a sequence of other methods provided by the class. Metrics for source code, used to assess source code complexity, maintainability, and testability, among other characteristics. Complexity metrics measure the logical complexity of source code, can also be applied to component-level design. Length metrics provide an indication of the size of the software. Metrics for testing. Statement and branch coverage metrics lead to the design of test cases that provide program coverage. Defect-related metrics focus on defects, that is, bugs, found rather than on the tests themselves. Testing effectiveness metrics provide a real-time indication of the effectiveness of tests that have been conducted. In-process metrics, process-related metrics that can be determined as testing is conducted. Metrics for maintenance. Software Maturity Index, SMI, provides an indication of the stability of a software product based on changes that occur for each release. SMI equals MT minus FA plus FC plus FD divided by MT, where MT modules in the current release, FA stands for modules in the current release that have been added, FC stands for modules in the current release that have been changed, and FD modules from the preceding release that were deleted in the current release. The average time to produce a release of software product can be correlated with the SMI. Quality Management Models. ISO, International Standard Organization. The ISO 9001:2015 standard, the latest in the periodically updated ISO standard, concerns the quality systems that are assessed by outside auditors, and it applies to many kinds of production and manufacturing organizations, not just software. It covers documentation, design, development, production, testing, installation, servicing, and other processes. The full set of standards consists of ISO 9001:2015, Quality Management Systems Requirements, ISO 9000:2015, Quality Management Systems Fundamentals and Vocabulary, ISO 9004:2009, Quality Management Systems Guidelines for Performance Improvements, ISO 19011:2011, Guidelines for Auditing Management Systems. To be ISO 9001 certified, a third-party auditor assesses an organization, and certification is typically good for about 3 years, after which a complete reassessment is required. Note that ISO certification does not necessarily indicate quality products. It indicates only that documented processes are followed. There are also other software-related ISO standards such as ISO IEC 25010:2011, which includes a quality in use model composed of 5 characteristics and a product quality model that covers 8 main characteristics of software. Also see http://www.iso.org for the latest information. ISO IEC 25010 is a software quality evaluation standard that defines quality in use model of 5 characteristics that relate to the outcome of interaction when a product is used in a particular context of use. Product quality model composed of 8 characteristics that relate to static properties of software and dynamic properties of the computer system. ISO IEC IEEE 29119 series of standards for software testing. ISO IEC IEEE 29119-1 Concepts and Definitions, published September 2013. ISO IEC IEEE 29119-2 Test Processes, published in September 2013. ISO IEC IEEE 29119-3 Test Documentation, published September 2013. ISO IEC IEEE 29119-4 Test Techniques, expected, published in late 2014. ISO IEC IEEE 29119-5 Keyword-Driven Testing, published in 2015. Quality Assurance and Standards. Standards are the key to effective quality management. They may be international, national, organizational, or project standards. Product standards define characteristics that all components should exhibit, that is, a common programming style. Process standards define how the software process should be enacted. Importance of standards. Encapsulation of best practices. Avoids repetition of past mistakes. Framework for quality assurance process. It involves checking standard compliance. Provide continuity. New staff can understand the organization by understanding the standards applied. Documentation standards. Particularly important documents are the tangible manifestation of the software. Documentation process standards. How documents should be developed, validated, and maintained. Document standards. Concerned with document identification, structure, presentation, changes highlighting, etc. Document interchange standards. How documents are stored and interchanged between different documentation systems. XML is an emerging standard for document interchange which will be widely supported in future. Development of process standards. The accompanying figure shows the development of process standards to get the improvised standards. ISO 9000. The four ISO 9000 models for quality systems can be depicted as shown. The ISO 9001 model depicts all activities from researching, designing, building, shipping, installing, and servicing. The ISO 9002 model guarantees production, installation, and servicing. The ISO 9003 model is restricted to inspection and testing. The ISO 9004 or 9004-2 model deals with customer interface activities and service quality improvement. International set of standards for quality management: ISO 9000-2000, ISO 9001-2000, ISO 9004-2000, etc. Applicable to a range of organizations from manufacturing to service industries. The ISO 9001-2000 specifies requirements for a quality management system for any organization that needs to demonstrate its ability to consistently provide a product that meets customer satisfaction. It integrates previous standards of ISO 9001, ISO 9002, and ISO 9003. ISO 9001 is a generic model that must be instantiated for each organization. ISO 9004-2000 provides guidance for continual improvement of a quality management system to benefit all parties through sustained customer satisfaction. It should be used to extend the benefits obtained from ISO 9001-2000 to all parties that are interested in or affected by the business operations. ISO 9000 certification. Quality standards and procedures should be documented in an organizational quality manual. External body may certify that an organization quality manual conforms to ISO 9000 standards, namely ISO 9001. Customers are increasingly demanding that suppliers are ISO 9000 certified. ISO 9000 and quality management. The below figure shows the quality management of ISO 9000 model. SPICE, Software Process Improvement and Capability Determination. An international collaboration to develop a standard and software process assessment, carried out under the Joint Technical Committee of ISO and the International Electrotechnical Committee, IEC, culminated in a new international standard in the 1998 timeframe, ISO IEC PDTR 15504. SPICE goals and scope. Overall goals of the standard are to encourage organizations to employ proven and consistent methods, reliable methods for assessing the state of their processes, use their assessment results as part of coherent improvement program. The scope is process assessment, process improvement, and capability determination. Software process domains to be assessed are acquisition, supply development, operation, maintenance, supporting processes, and service support. In June 1993, SPICE project organization was established with a mandate from JTC1, SC7 to assist to develop initial working drafts, undertake user trials to gain early experience, create market awareness, and take up. In January 1995, the period of user trials commenced. User trials continue today, and working drafts of the various parts of the proposed standard continue to evolve. In June 1995, the SPICE project organization completed its task of producing the set of working drafts to form the basis of technical report. SPICE concepts. A set of practices forms the lowest level of the standard's architecture. The architecture distinguishes between base practices, which are the essential activities of a specific process, generic management practices applicable to any process, which represent the activities necessary to manage a process and improve its capability to perform. The SPICE architecture model contains 5 process categories: customer-supplier, processes that directly impact the customer, support development and transition of the software to the customer, and provide for its correct operation and use. Engineering, processes that directly specify, implement, or maintain a system and software product and its user documentation. Management, processes which establish the project and coordinate and manage its resources. Support, processes which enable and support the performance of other processes on a project. Organization. Processes which establish the business goals of the organization and develop the process, product, and resource assets necessary to achieve its goals. IEEE, Institute of Electrical and Electronics Engineers. It creates standards such as IEEE Standard for Software Test Documentation, IEEE ANSI Standard 829, IEEE Standard of Software Unit Testing, IEEE ANSI Standard 1008, and others. IEEE Standard for Software Quality Assurance Plans, IEEE ANSI Standard 730, and others. Standard. Description. IEEE 829, a standard for the format of documents used in different stages of software testing. IEEE 4-1061, a methodology for establishing quality requirements, identifying, implementing, analyzing, and validating the process and product of software quality metrics. IEEE 1059, Guide for Software Verification and Validation Plans. IEEE 1008, as standard for unit testing. IEEE 1012, as standard for software verification and validation. IEEE 1028, as standard for software inspections. IEEE 1044, as standard for the classification of software anomalies. IEEE 1044-1, a guide for the classification of software anomalies. IEEE 830, a guide for developing system requirement specifications. IEEE 730, a standard for software quality assurance plans. IEEE 1061, a standard for software quality metrics and methodology. IEEE 12207, a standard for software lifecycle processes and lifecycle data. Scope. This standard applies to the development of a software quality assurance plan, SQAP. An assessment should be made for the specific software item to assure adequacy of coverage. Where the standard is invoked for an organization or project engaged in producing several software items, the applicability of the standard should be specified for each of the software items. Purpose. The purpose of this standard is to provide uniform minimum acceptable requirements for preparation and content of software quality assurance plans. In considering adoption of this standard, regulatory bodies should be aware that specific application of this standard may already be covered by one or more IEEE or ANSI standard documents relating to quality assurance, definitions, or other matters. It is not the purpose of this document to supersede, revise, or amend existing standards directed to specific industries or applications. Content conformance to this standard can be claimed when all requirements are carried out as defined in this standard. Format conformance to this standard can be claimed if the resulting SQAP is in the format specified. Software Quality Assurance Plan SQAP shall be approved by the manager of each unit of the organization having responsibilities defined within the SQAP or their designated representatives. SQAP Management describes the project organization structure, its tasks, and its roles and responsibilities. Depicts the organizational structure that influences and controls the quality of the software. Organizational structure that influences and controls the quality of the software. This shall include a description of each major element of the organization, together with the roles and delegated responsibilities. The amount of organizational freedom and objectivity to evaluate and monitor the quality of the software and to verify problem resolutions shall be clearly described and documented. Tasks this section shall describe that portion of the software lifecycle covered by the SQAP, the tasks to be performed, the entry and exit criteria for each task, the relationships between these tasks and the planned major checkpoints, the sequence and relationship of tasks and the relationship to the project management plan master schedule shall be indicated. CMM, Capability Maturity Model. The Software Engineering Institute, SEI, has developed a comprehensive model predicated on a set of software engineering capabilities. Capability Maturity Model, CMM, is a benchmark for measuring the maturity of an organization's software process. CMM defines 5 levels of process maturity based on certain key process areas, KPA, that are Level 1, Initial, Level 2, Repeatable, Level 3, Defined, Level 4, Managed, Level 5, Optimizing. Initial software process is characterized as ad hoc and occasionally even chaotic. Few processes are defined and success depends on individual effort. Repeatable. Basic project management processes are established to track cost, schedule, and functionality. The necessary process discipline is in place to repeat earlier successes on projects with similar applications. Defined. The software process for both management and engineering activities is documented, standardized, and integrated into an organization-wide software process. It includes all characteristics of Level 2. Managed. The software process and products are quantitatively understood and controlled using detailed measures. It includes all characteristics of Level 3. Optimizing. Continuous process improvement is enabled by quantitative feedback from the process and from testing innovative ideas and technologies. It includes all characteristics of Level 4. SEI has associated key process areas, KPAs, with each of the maturity levels. Each KPA is described by identifying the following characteristics. Goals, the overall objectives that the KPA must achieve. Commitments, requirements, imposed on the organization that must be met to achieve the goals or provide proof of intent to comply with the goals. Abilities, those things that must be in place organizationally and technically to enable the organization to meet the commitments. Activities, the specific tasks required to achieve the KPA function. Methods for monitoring implementation, the manner in which the activities are monitored as they are put into place. Methods for verifying implementation, the manner in which proper practice for the KPA can be verified. 18 KPAs, each described using these characteristics, are defined across the maturity model and mapped into different levels of process maturity. SEI has associated key process areas, KPAs, with each of the maturity levels. Each KPA is described by identifying the following characteristics. Goals, the overall objectives that the KPA must achieve. Commitments, requirements, imposed on the organization that must be met to achieve the goals or provide proof of intent to comply with the goals. Abilities, those things that must be in place organizationally and technically to enable the organization to meet the commitments. Activities, the specific tasks required to achieve the KPA function. Methods for monitoring implementation, the manner in which the activities are monitored as they are put into place. Methods for verifying implementation, the manner in which proper practice for the KPA can be verified. 18 KPAs, each described using these characteristics, are defined across the maturity model and mapped into different levels of process maturity. The following KPAs should be achieved at each process maturity level. Process maturity level 2, software configuration management, software quality assurance, software subcontract management, software project tracking and oversight, software project planning, requirements management. Process maturity level 3, peer reviews, intergroup coordination, software product engineering, software management, training program, organization process definition, organization process focus. Process maturity level 4, software quality management, quantitative process management. Process maturity level 5, process change management, technology change management, defect prevention. Each of the KPAs is defined by a set of key practices that contribute to satisfying its goals. The key practices are policies, procedures, and activities that must occur before a key process area has been fully instituted. The SEI defines key indicators as those key practices or components of key practices that offer the greatest insight into whether the goals of a key process area have been achieved. Software configuration management, SCM. Goal is to maximize productivity by minimizing mistakes caused by confusion when coordinating software development. SCM identifies, organizes, and controls modifications to the software being built by a software development team. SCM activities are formulated to identify change, control change, ensure that change is being properly implemented, and report changes to others who may have an interest. SCM is initiated when the project begins and terminates when the software is taken out of operation. View of SCM from various roles. Project Manager, an auditing mechanism. SCM Manager, a controlling, tracking, and policy-making mechanism. Software Engineer, a changing, building, and access control mechanism. Customer, a quality assurance and product identification mechanism. Baseline, an SCM concept that helps practitioners to control change without seriously impeding justifiable change. Baseline, IEEE definition, a specification or product that has been formally reviewed and agreed upon, that thereafter serves as the basis for further development and that can be changed only through formal change control procedures. A baseline is a milestone in the development of software. Software configuration item SCI is information that is created as part of the software engineering process. As the software process progresses, the number of SCIs grows rapidly. System specification spawns a software project plan and software requirement specification. Baseline process. A series of software engineering tasks produces an SCI. Software configuration items and the approval of these SCIs that is obtained through a formal technical review. The approved SCI is given a new version number and placed in a project database, that is, software repository. A copy of the SCI is taken from the project database and examined or modified by a software engineer. The baseline of the modified SCI goes back to the formal technical review. For example, all parts design specifications have been reviewed, corrected, and then approved. The design specification becomes a baseline. After SCIs are reviewed and approved, they are placed in a project database or project library or software repository. Software configuration items. SCI could be considered to be a single section of a large specification or one test case in a large suite of tests. SCI is a document, an entire suite of test cases, or a named program component, that is, a C++ function or an ADA package. SCIs are organized to form configuration objects that may be cataloged in the project database with a single name. A configuration object has a name, attributes, and is connected to other objects by relationships. SCM repository. It is a set of mechanisms and data structures that allow a software team to manage change. It acts as a center for both accumulation and storage of software engineering information. Software engineers use tools integrated with the repository to interact with it. Functions of an SCM repository. Data integrity. Validates entries, ensures consistency, cascades modifications. Information sharing. Shares information among developers and tools, manages and controls multi-user access. Tool integration. Establishes a data model that can be accessed by many software engineering tools, controls access to the data. Data integration allows various SCM tasks to be performed on one or more CSCIs. Methodology enforcement defines an entry relationship model for the repository that implies a specific process model for software engineering. Document standardization defines objects in the repository to guarantee a standard approach for creation of software engineering documents. Toolset used on a repository. Versioning. Save and retrieve all repository objects based on version number. Dependency tracking and change management. Track and respond to changes in the state and relationship of all objects in the repository. Requirements tracing. Forward tracing. Track the design and construction components and deliverables that result from a specific requirement specification. Backward tracing. Identify which requirement generated any given work product. Configuration management. Track a series of configurations representing specific project milestones or production releases. Audit trails. Establish information about when, why, and by whom changes are made in the repository. SCM tasks. Identification, change control, version control, configuration auditing, status reporting. Identification task. Identification separately names each CSCI and then organizes it in the SCM repository using an object-oriented approach. Objects start out as basic objects and are then grouped into aggregate objects. Each object has a set of distinct features that identify it. A name that is unambiguous to all other objects, a description that contains the CSCI type, a project identifier, and change and for version information. List of resources needed by the object realization, that is, the document, the file, the model, etc. Change control task. Change control is a procedural activity that ensures quality and consistency as changes are made to a configuration object. A change request is submitted to a configuration control authority, which is usually a change control board. The request is evaluated for technical merit, potential side effects, overall impact on other configuration objects and system functions, and projected cost in terms of money, time, and resources. An engineering change order (ECO) is issued for each approved change request. Describes the change to be made, the constraints to follow, and the criteria for review and audit. The baseline CSCI is obtained from the SCM repository. Access control governs which software engineers have the authority to access and modify a particular configuration object. Synchronization control helps to ensure that parallel changes performed by two different people don't overwrite one another. Version control task. Version control is a set of procedures and tools for managing the creation and use of multiple occurrences of objects in the SCM repository. Required version control capabilities. An SCM repository that stores all relevant configuration objects. A version management capability that stores all versions of a configuration object or enables any version to be constructed using differences from past versions. A make facility that enables a software engineer to collect all relevant configuration objects and construct a specific version of the software. Issues tracking, bug tracking capability that enables a team to record and track the status of all outstanding issues associated with each configuration object. The SCM repository maintains a change set, serves as a collection of all changes made to a baseline configuration, used to create a specific version of the software, captures all changes to all files in the configuration, along with the reason for changes and details of who made the changes. Configuration auditing task. Configuration auditing is an SQA activity that helps to ensure that quality is maintained as changes are made. It complements the formal technical review and is conducted by the SQA group. It addresses the following questions. Has the change specified in the ECO been made? Have any additional modifications been incorporated? Has a formal technical review been conducted to assess technical correctness? Has the software process been followed, and have software engineering standards been properly applied? Has a change been highlighted and documented in the CSCI? Have the change data and change author been specified? Do the attributes of the configuration object reflect the change? Have SCM procedures for noting the change, recording it, and reporting it been followed? Have all related CSCIs been properly updated? A configuration audit ensures that the correct CSCIs by version have been incorporated into a specific build, that all documentation is up to date and consistent with the version that has been built. Status reporting task. Configuration status reporting, CSR, is also called status accounting. Provides information about each change to those personnel in an organization with need-to-know answers: what happened, who did it, when did it happen, and what else will be affected. Sources of entries for configuration status reporting. Each time a CSCI is assigned new or updated information, each time a change is approved by the CUCB and an ECO issued, each time a configuration audit is conducted, the configuration status report, placed in an online database or on a website for software developers and maintainers to read, given to management and practitioners to keep them appraised of important changes to the project CSCIs. Types of errors. User interface errors. Missing, wrong functions, doesn't do what the user expects, missing information, misleading, confusing information, wrong content in help text, inappropriate error messages. Performance issues. Poor responsiveness, can't redirect output, inappropriate use of keyboard. Boundary-related errors. Boundaries in loop, space, time, memory, mishandling of cases outside boundary. Calculation errors. Bad logic, bad arithmetic, outdated constants, calculation errors, incorrect conversion from one data representation to another, wrong formula, incorrect approximation. Initial and later states. Failure to set data item to 0, to initialize a loop control variable, or reinitialize a pointer, to clear a string or flag incorrect initialization. Control flow errors. Wrong returning state assumed, exception handling based exits, stack underflow, overflow, failure to block or unblock interrupts, comparison sometimes yielding wrong result, missing, wrong default, data type errors. Errors in handling or interpreting data. Unterminated null strings, overwriting a file after an error exit or user abort. Race conditions. Assumption that one event or task finishes before another begins. Resource races. Task starts before its prerequisites are met. Messages cross or don't arrive in the order sent. Load conditions. Required resources are not available. No available large memory area. Low priority tasks not put off. Doesn't erase old files from mass storage. Doesn't return unused memory. Hardware. Wrong device, device unavailable, underutilizing device intelligence, misunderstood status or return code, wrong operation or instruction codes. Source, version and ID control. No title or version ID, failure to update multiple copies of data or program files. Testing errors. Failure to notice, report a problem, failure to use the most promising test case, corrupted data files, misinterpreted specifications or documentation, failure to make it clear how to reproduce a problem, failure to check the unresolved problems just before release, failure to verify fixes, failure to provide summary report. Conclusion. In this chapter, we have covered the following in detail. Basic software quality parameters and its metrics, software configuration change, types of errors, quality management models, ISO, SPICE, IEEE, CMM.